In the evolving landscape of sustainable urban development, the construction of bioclimatic skyscrapers stands as a testament to the power of interdisciplinary collaboration. As construction engineers, architects, and eco-engineers, we are united by the challenge of orchestrating living, adaptive structures that harmonize with their environment while meeting the complex demands of modern cities. The integration of advanced computational methods, specifically quantum-enhanced joint embedding predictive architectures, quantum JEPA, offers a transformative approach to this challenge, enabling us to optimize every decision for sustainability, efficiency, and human well-being. Let us begin by considering the fundamental complexity of a bioclimatic skyscraper. Such a building is not merely a stack of floors, but a dynamic ecosystem. It features vertical gardens, natural ventilation shafts, rainwater harvesting systems, solar panels, and a diverse array of programmatic spaces: gyms, restaurants, offices, and residences. Each of these elements interacts with the others, creating a web of dependencies and opportunities. The task of planning, scheduling, and adapting construction in this context is daunting, as the number of possible action sequences grows exponentially with each new variable. Traditional project management tools, while powerful, are limited by their sequential, deterministic nature. They can only evaluate a small subset of possible plans, often relying on heuristics or simplified models. In contrast, quantum JEPA leverages the principles of quantum superposition and amplitude amplification to explore the entire landscape of possibilities in parallel, identifying optimal strategies that would be inaccessible to classical computation. Quantum state encoding, capturing the building's complexity. At the heart of the quantum JEPA approach is the encoding of the building's current state as a quantum state vector. This represents how the building's current state is captured in the quantum system. Think of it like a detailed digital twin that includes everything about the building: the status of each floor, finished, in progress, etc., the state of gardens on each level, the ventilation system status, water systems readiness, resource availability, team assignments. It's like having a complete snapshot of the building that captures thousands of details all at once, with each possible configuration weighted by how likely or valuable it is. This encoding allows us to represent in a single quantum state the entire spectrum of what the building could be at any given moment. It is a living snapshot, constantly updated as new information arrives from the site, supply chain, and environment. Superposition of action plans, exploring every possibility. The next step is to consider the set of all possible next actions. In a project of this scale, the options are vast. Should the landscape team advance to the 25th floor, or should the MEP team install rainwater tanks before the forecasted storm? Should the restaurant fit-out be prioritized, or should resources be shifted to complete the natural ventilation shafts? Each decision has cascading effects on the schedule, resource utilization, and ecological performance of the building. In the quantum paradigm, these actions are not evaluated one by one, but are placed into a superposition. This means that the quantum system is, in effect, exploring every possible plan simultaneously. This describes how all possible construction plans are considered simultaneously. Instead of evaluating one plan at a time, like traditional methods, the quantum system puts all plans into a state where they exist at the same time. It's similar to considering every possible move in a chess game at once, rather than analyzing each move sequentially. This allows the system to process millions of potential scheduling and resource allocation options in parallel. This superposition is not merely a theoretical construct. It is the engine that allows quantum JEPA to evaluate millions of possible strategies in parallel, rather than being limited to a handful of scenarios. Quantum prediction operator, simulating outcomes. With the building state and action plans encoded, we apply the quantum prediction operator. This operator acts on the combined state of the building and the action plan, simulating the outcome of each possible sequence. For example, it can predict how installing a gym on the 15th floor will affect energy use, or how planting native species on a sky terrace will influence biodiversity and microclimate. This represents how the system simulates what would happen if each possible plan were implemented. The operator takes the current building state and all possible action plans and predicts the outcome of each scenario. It's like having a super-powered construction simulator that can instantly show you the results of every possible decision you might make, how it would affect energy use, plant growth, team coordination, and project timeline. The prediction operator incorporates the physical, ecological, and logistical models developed by the engineering and design team. It accounts for the flow of materials, the sequencing of trades, the growth of plants, the operation of mechanical systems, and the interactions between all these elements. The result is a quantum state that encodes the predicted outcome of every possible plan in parallel. Scoring function, evaluating project priorities. To evaluate these outcomes, we employ a scoring function. This function is a weighted sum of the project's priorities: sustainability, biodiversity, energy efficiency, occupant comfort, cost, and schedule adherence. Each outcome is assigned a score based on how well it advances our ecological and operational goals. This shows how each potential outcome is evaluated based on what matters most for the project. The system assigns scores based on sustainability performance, biodiversity, impact, energy efficiency, occupant comfort, schedule adherence, cost effectiveness. The project team assigns weights to determine which factors are most important. A highly ecological project might prioritize sustainability and biodiversity, while a commercial project might emphasize schedule and cost. The scoring function is implemented as a quantum operator, acting on the outcome state to assign higher amplitudes to plans that better fulfill the project's criteria. Amplitude, amplification, focusing on the best plans. At this stage, we invoke amplitude amplification, a quantum process analogous to Grover's algorithm. This step increases the probability of selecting high-scoring plans when the quantum state is measured. The amplification operator acts only on those plans whose scores exceed a certain threshold, boosting their amplitudes while suppressing less desirable options. This represents the process of focusing on the best construction plans. After evaluating all possible plans, the system uses a quantum technique to boost the probability of selecting high-scoring options while reducing the chances of choosing lower-scoring ones. It's like having a filter that automatically brings the best options to the top and pushes less desirable ones to the bottom. The mathematics of this process involves a reflection about the mean amplitude, followed by a selective phase inversion for the best plans. After several rounds of amplification, the quantum state is dominated by the most promising action sequences. Measurement, making the optimal decision. When we perform a measurement, analogous to making a decision on site, the superposition collapses and we obtain a single, concrete plan. The probability of selecting an optimal plan is now maximized thanks to the prior amplification. This describes the final selection process. When it's time to make a decision, the quantum system collapses from considering all possibilities to selecting a single optimal plan. The probability of selecting any particular plan is based on its score. The better the plan, the more likely it is to be chosen. This is like finally making your move in chess after considering all possibilities, but with a weighted probability that favors the strongest moves. Practical example: adaptive planning in a living building. Let us consider a practical example. The building is at mid-height, with gardens installed up to the 20th floor, gyms and restaurants planned for the next 10 floors, and a forecast of heavy rain in 2 days. The quantum JEPA system encodes all this information, along with the availability of teams and materials. It then explores every possible way to coordinate the next week's work. Should the landscape team prep the 25th floor, or should the MEP team install rainwater tanks before the storm? Should the restaurant fit-out be advanced, or should resources be shifted to complete the natural ventilation shafts? How will each decision affect energy use, biodiversity, occupant comfort, and the project schedule? The system predicts the outcome of each plan, scores them according to the project's ecological and operational priorities, and amplifies the best. Within seconds, it delivers a coordinated multi-team action plan that maximizes green coverage, minimizes risk, and keeps the project on schedule. Dynamic adaptation, responding to change. One of the most powerful features of quantum JEPA is its ability to adapt instantly to changing conditions. Suppose a shipment of native plants arrives early, but a crane breaks down. The system updates the quantum state to reflect the new reality, re-encodes the set of possible actions, and reapplies the prediction, scoring, and amplification steps. Within moments, it produces a new optimal plan, reallocating teams and resources to maintain progress and ecological integrity. This dynamic adaptation is essential in the real world, where construction projects are subject to constant change. Weather, supply chain disruptions, labor availability, and unforeseen challenges. Quantum JEPA provides the agility to respond intelligently, ensuring that the project remains on track and aligned with its sustainability goals. Interdisciplinary collaboration, integrating expertise. The success of this approach depends on the close collaboration of construction engineers, architects, and eco-engineers. Each discipline contributes its expertise to the models that underpin the quantum operators. Construction engineers provide detailed models of structural sequencing, resource allocation, and logistics. Architects define the spatial and programmatic requirements, ensuring that the building meets its functional and aesthetic goals. Eco-engineers model the growth of plants, the flow of water and air, and the interactions between the building and its environment. These models are integrated into the quantum JEPA system, ensuring that every plan is evaluated holistically with full consideration of structural, ecological, and human factors. Mathematical summary: the quantum JEPA pipeline. To summarize, the quantum JEPA process can be represented as a sequence of steps. 1. State preparation. Capture the current building state and all possible action plans. 2. Prediction. Simulate what would happen with each possible plan. 3. Scoring. Evaluate each outcome based on project priorities. 4. Amplitude. Amplification. Boost the probability of selecting the best plans. 5. Measurement. Make a final decision, selecting one optimal construction plan. This quantum approach allows construction teams to consider vastly more possibilities than traditional methods, leading to better decisions that balance sustainability, efficiency, and human needs in complex eco-skyscraper projects. Vision for the future: living adaptive buildings. Quantum JEPA represents a new philosophy of construction management, one that treats the building as a living, evolving ecosystem. By leveraging the power of quantum computation, we can evaluate millions of possible plans in parallel, adapt instantly to change, and realize our vision of buildings that are not only efficient and resilient, but also regenerative and harmonious with nature. As construction engineers, architects, and eco-engineers, we are at the forefront of this transformation. Our collaboration, informed by rigorous mathematics and guided by ecological principles, enables us to create structures that are both technologically advanced and deeply connected to their environment. The future of sustainable construction is quantum, and together we are building it. one living skyscraper at a time.